click on the start streaming button, and it should show up in about 10 more seconds. So I'm gonna wait a little bit until that part is started up. Alrighty. Alright, so let's go ahead and work on the program first. Okay, so this is the first thing we do, is to work on the, okay, thank you, Julian. So what we'll do is we'll work on the lab that you did over the weekend, and hopefully everybody got a chance to work on it, because that really is your first programming task, not counting the floating point thing in assembly. So, the floating point thing is hopefully was reapplying what you already have learned in CISP310 in order to solve a particular problem in representing values. But what this homework assignment is about, the absolute value homework assignment, that is really just kind of new programming, as far as you're concerned. So we'll take a look at the code. So I'm going to use NVim. I'm not sure how many of you experimented with NeoVim, which I use extensively. So we'll take a look at this program. I'm going to call this program abs.ttpasm, and the extension is important in this case because the syntax highlighter relies on the extension to determine what syntax rules to use. Alright, so typically what I do when I write a program is I just write down, in comments what the program is supposed to do. So in this particular case, we need to find the absolute value. So I'm just going to write down the C code for this same subroutine. So we have int abs, and we have an input that is an integer. So I'm not even bothering to write down the types at this point. Okay, so all of this is part of the comment, and I use a single return statement in this case, and return is highlighted because it is a very important key concept in assembly language programming. So I made the syntax rule highlight certain words even if they only show up in comments. So in this case, I want to return depending on whether x is less than 0 or not. If it is less than 0, I want to return the arithmetic negation of x. Otherwise, I just need x itself without negating it first. Okay, so that's basically one way to represent the absolute value function. And this is using the ternary operator, which we discussed already in class. So now the question is, how do we do this in assembly? So I'm not sure how many of you, wrote the entire program all at once, without testing it in between, or how many of you actually wrote it in smaller pieces. So I think it is really a good idea to write it in smaller pieces. In other words, you try to confirm that it gets a particular thing done first before you rely on that assumption to work further into the program. So I'm going to show you a little bit of that. I cannot make it really step by step today because I got other things that I need to talk about today, but I can show you a little bit first. So the first thing we want to do is to determine whether x is less than 0. And according to the lab instructions, you can use a quote-unquote test instruction to see if the sign flag is on or not. And then we talked about the computer toy processor architecture within the ALU. As long as you make it go through some sort of calculation and it's not increment or decrement, the flags, certain flags will be set. The two flags that are always going to be affected by the result, not counting increment and decrement again, are the Z flag, which is the 0 flag, which is not very useful in this case, and also the sign flag, which is really useful in this case, because when the sign flag of the difference is a 1, that means the result is negative. Now, but that doesn't even have to be a subtraction instruction. All instructions will do that. So in this case, the AND instruction, conjunction, would actually do that. So if you use an instruction like AND AA, it is going to force register A from the register bank to go through the AND gate inside the ALU. So A is presented as both inputs of the AND gate, which means the output of the AND gate is just going to be whatever register A has. So it doesn't really do a single thing to change the value of register A. But in the process of doing this, it has a side effect that is very important, because if register A has bit 7, the most significant bit being a 1, then the sign flag will be set. Okay, so this is the one thing that we want to test first, is to make sure that when we do something like this, the sign flag is affected, because otherwise it doesn't matter what we do, to negate the value of x, because we cannot determine first whether x is less than 0 or not. Okay, so that's the first thing we want to do, is really just to look at the instruction of AND. All right, so I'm going to take the editor off screen right now, and instead I'm going to start up LogicSim. So we can do this in a few ways. The first way is to just run LogicSim in GUI mode, so that this way we can just single clock through the whole thing. When your program only has 1 or 2 instructions, it's okay to do it that way. But as your program gets longer, like this program will get about, I think, when all things are done, you're going to have about 9 or 10 lines of code, which is not really long in any way. The actual core part of taking the absolute value should have about 7 instructions, and that includes label definitions as well. But even so, it is tedious to have to go through the GUI to look at the effect of the program. So my recommendation is to use the log analyzer, just as a tool, because then you can actually visualize how things got changed as we execute the program. So you got your choices here. All right, so what we do is we're going to start up LogicSim, and let me see if the last Java would do it. Yep. So then we start up LogicSim and the processor file. All right, so with a single instruction like just AND AA, I can even do this without using the assembler, because it is probably a good practice to go back to the opcode table, because that's one thing that you want to keep handy when you are taking the test, which is on this Thursday, is to have all of these documents already at your fingertip. If you are a paper person, my recommendation is to print out all the documents that you think might be helpful, and have that stack of paper available to you, possibly with even post-its to kind of help you identify where each important document is. Okay, and you can use a syntax highlighter. You can also make editing within the document itself before you print it out. So you got a lot of options over there. So we want to look up, in this case, we want to look up AND instruction. The AND instruction is right here, and it starts with a 1100, which is C in hexadecimal. And because we want register A for both X and Y, so that means XX is 00, YY is also 00. So C0 is the instruction that we want to use. So now we get back into LogicSim, and I'm just making sure that it fits right within the window that OBS is capturing. There we go. So now we go to here, we type C0. And if you really want to make sure that the program stops executing instead of keep going and going and going, you can always force to have a 01 as the next opcode. So this way we have an AND AA followed by a halt instruction. The halt instruction has an opcode of 01. All right, so we can test the program as is. Okay, that's so. But if we do it as is, okay, we need to look at the register bank. Register A is 00. So the most significant bit is 0. So after this, we are expecting the sign flag to be a 0. Okay. Now, on the other hand, if you just want to test, what if register A is 80, which is 1 followed by 7 zeros, that makes the sign bit a 1 in register A. You can do that too. So you can basically inject a value before you test it. And this is one of the nice things of testing certain code in GUI mode, is you can inject values into the registers before you run your code, or even halfway through running your code, you can alter the value in the register. But you cannot do that using the trace method. The trace method is basically just running your program, generate a trace, and then you can use the trace analyzer to look at the trace and find out what exactly happened when you ran the program. All right, so let's go ahead and test this code. And to test the code, we have to kind of keep an eye on the ROM as well, because we want to make sure that we capture the right event at the right time. So we are going to have 4 control T's right away, just to get into the microcode slice that implements the AND instruction. So once again, when I use the word implement, it is the microcode or the ROM location where the output of that ROM location is configuring all the demultiplexers, multiplexers, registers, RAM, and all the other components so that it accomplish a particular task. And in this case, the task that we're trying to accomplish is to find out what is the bitwise AND of A and put the result back into A. But that doesn't sound very useful. But the useful part is it sets certain flags, including the important flag called the sign flag. So what I'll do is I'll control T exactly 4 times. Okay, 1, 2, 3, 4. So now we can see that in the ROM it is now at location C00, where it has a very specific output in hexadecimal. It is 154C498. But what we can do, once we have the logic sim which you can use during the exam. Okay, so all the tools that I use in class, you can use those in the exam as well. So you can fire up logic sim, you can fire up the processor emulator, and use that as a resource to help you answer the questions. So right now, what are we doing? Well, let's check it out. Okay. We can see the green wires are the light green wires are the important ones. So we know that we are enabling the input to the register bank because it wants to update register A. And what it is using to update register A is register A itself, which is 80, and this is verifying that is the case. So this is not really the interesting part. The interesting part is how is it affecting the flags register. So this is the flags register. We can see the flags register is enabled. In other words, it is about to be updated. And right now it is 00. So right now the content of the flags register has every single flag cleared. So the carry flag, which is also the borrow flag, is cleared. The Z flag is cleared. The sign flag is cleared. The overflow flag is cleared. And then the L flag is also cleared. They're all cleared. So when we look at the input into the flags register, which is the output, we can see that 2 of the 5 flags are about to be changed from 0 to 1. The least significant bit is the carry. This is the 0 flag. This is the sign flag. Okay, so the sign flag is bit 2 of the flags register, and then we have the overflow flag. And then the exclusive OR between the overflow and the sign flag becomes the L flag, which is bit 4, which is also the most significant bit of the flags register, because the flags register only has 5 bits. Okay, so now we know that the method works. Okay, so if I control T again, this basically goes through the implementation of the instruction, and we can see how the flags register is updated to 1-4. If you convert 1-4 from hexadecimal into binary, you will see that it will give you exactly this particular bit pattern, which is 1 followed by 0100 in binary. So by going through this step first, okay, I now go back to my program, and let me do this. So now I have confirmed that this method does reflect, it captures the sign flag of register A. So once we know that, we can now use a conditional branch instruction that is sensitive to the sign flag. So JSI is the instruction used, not JOI, not JLI, it is just JSI. Now, if you use JLI, it might work too, but it is the wrong flag to use. Okay, so the proper flag to use in this case is JSI. So now we look at this and we go to a particular label. So unless you want to count instructions location by location and come up with the exact number, I would much rather use a label, and you can make the label more meaningful, and you can say negative. Okay, so now we define negative at some point, and this is the way I do it. Is I basically just write down the label definition as soon as I make a reference to it. So this way I know where it is supposed to be and what I'm supposed to do over there. So the first question is, if I continue execution over here, what does it mean? Now, this is something that I do personally. I'm not sure whether you find it useful or not, but if you do, you might want to do it when you're doing your own programming. Is after a conditional branch instruction, I would use a line of comment to remind myself what does it mean if I did not make the branch. Why is it better to use a label than a constant? I'm assuming Catherine is referring to negative as a label. Is that correct? Or are you okay? Yard. Okay, so it is easier this way because otherwise I have to count the number of locations. Yep, I know. It's okay. I got you. So if I don't use negative, okay, then I have to count the number of instructions between this. I have to first know where the JSI instruction is at, and then I have to count the number of bytes between the JSI instruction and where I'm supposed to go to. So it is rather tedious. I can show you guys how to do it after I'm done with this program, but right now I'm just going to use a label. So I will remind myself what it means to be here. I will just say that A is not negative. So if register A is not negative, then it doesn't really need to do anything because I just want to store the absolute value of register A in register A. So if register A is not negative, it is already its own absolute value, so there's nothing to do. I can now just put a halt instruction here to stop the program from continuing any further. On the other hand, if I get to negative, okay, A is negative at this point, okay? So now what do? I need to do the arithmetic negation. There are several ways to do it. For those people who really do not want to go through bitwise not +1, you can always put a 0 into a different register and then do a subtraction and then put the result back into register A. So there's always that approach. I will show you exactly what I mean by that. So we can do LDIB with 0, which is not really needed because all registers are reset to 0. But unless we can make that assumption, it's better, it's safer to initialize a register. And then what we can do is to perform a subtraction. So we'll subtract register A from register B. So if A is negative to begin with, now it will be exactly the same magnitude, but it will be a non-negative number or positive number for sure, because 0 is already captured here. So then we have to do a CPR, copy register, from register B back to A, because the assignment says we want to do an in-place operation, which means register A should contain its own absolute value from the beginning. So now we can have a halt instruction and we're done. Okay, but this is not necessary. Okay, this is one way to do it. It is somewhat intuitive because it is resembling what we would do on a piece of paper. On the other hand, if we already know what is 2's complement, then we can just perform 2's complement. 2's complement involves 1's complement, which is bitwise not, and then we add 1. So not A is going to perform a bitwise not of A and then put the result back into register A. So this is basically saying A equals to tilde A, because tilde A in C++ notation is bitwise not of A. Then we need an increment instruction, which is really just ++A in C notation, and we're done. Okay, so this is the actual program, and I have 2 extra lines here for the comments. If you do not include the comments, that is exactly 7 lines of code. And on top of that, the assignment says you need to define K1 as the constant that you would be using for testing. So if you just say K1 without anything else, and then you do a LDIA with K1, that will work. Except in this case, K1 is going to be 0, because this K1 definition that has no expression to the right hand side of the colon is defining K1 as a symbolic name of the location of whatever instruction is following it. And this is at the very beginning of the program, so that means register A is going to be 0 because K1 is 0 in this case. So if you want to test a program with some non-zero values, now you can put in something like you have to be careful because if you specify a value that is too large, it is actually going to be representing a negative value. I'll give you an example. Okay, 255. 255 looks like, sounds like, and it feels like a positive number, but in 8 bits signed representation, it is representing the value of -1. So you just have to kind of keep that stuff in mind, is what does this value look like as a bit pattern, okay? To be more specific, as an 8-bit bit pattern, okay? So you gotta kind of keep in mind of all that stuff. So we'll go ahead and test this program, and this time I'm going to use the other approach, which is using the trace analyzer. Now, one thing about the trace analyzer, and this is a bug of Logisim that I have not yet found time to fix yet, okay? So maybe at some point I will fix that bug. But at this point, the bug in Logisim prevents us from starting with any instruction other than a no-op instruction. It has no problem starting with the no-op instruction, but if I start with any other instruction, it does not work. So that does make the program one line longer than otherwise. So let me check out what Catherine has to say. So save the file first. Alright, so you can only use a high number for negative in this processor. I believe -1 works as well. So if you type in -1, I believe that works too. I think -4 should work. Well, we can give it a try, right? So that's we'll give it a try and see if that works. So -4. Now we should probably write down a comment here and basically say, what does -4 look like in if 255 is -1, what is -4? So -4 is 3 less than -1. So that means 255 minus 3 is 252. So they should be the same. If I define K1 to be 252, the program should run exactly the same way. So we'll give it a try. Okay, I think it works. I've seen it work before. All right, so we save the program, and then I have to do this part, because I am using the command line a lot. So I'm going to do this, and oops, pipe. There we go. So now the program is in the clipboard, and we go back to the browser first and go to the assembler. So the assembler is available to you as well, during the test. And I would just kind of make a fresh copy of the assembler sometime before the exam, just to make sure that the copy that you're using is the one that works. All right, so we'll erase whatever A has and then paste our program in. Make sure we don't have any errors. Okay, no errors. Then we go to RAM file and then download it. Okay, so we download as a CSV. TSV works as well, but it's just that I like to use CSV for this, so I can actually distinguish between the RAM file and also the log. All right, so I got this, and I'm going to switch back to Logisim. And I'm not going to, well, okay, you can run the program in Logisim too, but if the program doesn't work, it's really kind of difficult to debug the program. I'll show you what I mean by that. Okay, let's go ahead and load the image. It's abs.csv. So I got the program in, and I can type Control K this time to enable the automatic clocking until it gets to the halt instruction. So I do a Control K. And you can see that it is already at the halt instruction. How do we know? Because the halt pin is a 1. Okay, so that is a really clear sign that we can now stop clocking. So Control K again to stop the clocking. And if everything works the way it's supposed to, register A should now contain um, its own absolute value from K1, and K1 is -4. So that means when we look into register A, oh, we don't even need to look into it anymore if we just want to know what it is, because it is it's an output pin. So you can see register A in binary is 100, which is 4. So the program did work. It does take -4 as a constant. I could use 252 as well. The program would work exactly the same way. Even the binary code for the instructions would look exactly the same as well. Alright, so this is one way to test your program, is to run it in GUI mode, and then when it gets to the halt instruction, you look into the register bank and find out whether the register has the right value or not. So that's one way to do it. Now, if I close it and switch back to the command line, this time we'll try to run it using the command line version of Logisim. So the command line version of Logisim is starting with exactly the same stuff as the GUI mode, except you also have to supply some additional stuff. The first one is processor 0003.circ, because that is first loaded into Logisim. And then the next thing you need to do is to do a -tty to basically say, you're telling Logisim to go into the CLI mode, and you want it to output a table of its output. I do not know of any other option after TTY, so I think the original author planned to have some additional output, maybe not a table, maybe XML or JSON representation, but never got around to do it. And then you have to specify -load, because we are trying to load abs.csv, which is the RAM file that we downloaded from the assembler, into the actual RAM component. So when you're done with this part, you can press the enter key right now, except the output is going to be displayed in the CLI instead of being captured. But it's okay if you just want to confirm that it works. Okay. So once we have done this, it works, then we'll capture it into abs.tsv, which is the trace file. The T is not trace, by the way. The T is tab. Okay, so this is a tab separated value file. And then we can go back to the trace analyzer, which is also in the processor subfolder. Okay, so this is also a resource that you can utilize during the test. It's free for you to use. And over here we go to file, and then we go to import, upload, and then we specify it is abs.tsv. Click open. And then we have to make sure that we pick the right options. Replace current sheet, tab, and no. And then we click import. And when it's all done, we have to wait until the progress bar is done over here. Then we go to analysis, and we can see now the side effect of every single instruction, and we can see how register A is initialized to FC. FC in hexadecimal is 11111100. Okay, and if you take the 2's complement of that, it would become a 4. But we don't have to do it by hand, because this trace will show you exactly how we will take the 2's complement of register A. 03 is our AND instruction, and you can see how the AND instruction is changing the sign flag as well as the L flag. And then at 04 we have the conditional branch instruction, and the conditional branch instruction is taking up location 04 as well as location 05, but you can see that it does not continue execution at location 05 because the branch did happen. So it changes the PC, the program counter, to 07, and this is where we continue execution. This is where we perform the bitwise NOT of register A, so that's why A ends up as a 03. Now, does it make sense? Well, let's think about it. Register A was 11111100. If we turn all the ones into zeros and all the zeros into ones, then we end up with 00000011, which is 03 in hexadecimal. So that makes sense. 08, at the location 08, we have the increment instruction, which increments register A from 3 to 4. And then at the location 09, we have the second halt instruction, and that's why the program stopped. So the program did work correctly. Okay, this is a relatively simple program. But the trace analyzer, if the program did not work, the trace analyzer would have given me all the clues that I need in order to debug the program. And the best thing about the trace analyzer is you can go back and forth in time. It doesn't have to just go be forward. You can actually go backwards as well, because it logs everything that got changed in the process of executing the program. So do we have any questions about the lab at all? No. Okay, so I'm not seeing any questions. All right, so the scope of exam 2 does include assembly language programming. So this particular lab is within the scope of the exam. So that's the first thing I want to tell you guys, because I just want to make sure that people understand where do we stop. We are not going to talk about C control structures, which is what we'll be talking about tomorrow and the day after, because that is out of the scope of the exam. But for simple code like this, for finding the absolute value, it is in the scope. So are we good so far or not? Do we have any questions? All right, looks like we don't have any questions. All right, so if we don't have any questions, then we'll start to review other material that will be in the test. So one of those is the topic of double precision floating point number representation, or in short, doubles. Okay, that is also in the scope of exam 2. So what I can do is I can show you the last time I gave exam 2 to CISP310, what question I asked in that case. So I'm gonna use, I'm doing this off screen. I'm just typing the command off screen right now to get to that question. I think it's question number 3 of the previous time I have this exam. There we go. All right, so let me put this into the view area where it's going to be recorded. And we'll go ahead and zoom in a little bit, because there's no need to, we got some space. All right. So here's the text of the question. So in this question, we are converting a value to a double precision floating point number in hexadecimal. So you have to read the question very carefully, because if the answer is in binary, points will be taken off. Now, is it going to be a lot of points? Probably not, okay, because the conversion from hexadecimal to, from binary to hexadecimal is relatively simple, but nonetheless, okay, you have to answer the question as basically based on what you're being asked to present. So the next line is really important, or the next sentence is really important. Be sure to show all the steps using the space below the text. So that means, do not skip steps, okay? If you have a doubt and go like, well, do I need to include this? Well, put it in anyway, okay? Because you'll be typing, and most people can type much faster than they can write. And this is the kind of question that I ask when people are having face-to-face exams, where they have to actually handwrite everything. An answer without derivation will not receive points, okay? And some people did that last semester. They just gave me a hexadecimal number at the very end. Even if it was 100% correct, those people would still not be getting any points, because the question specifically asks about the derivation, okay? And an answer with incomplete steps will not receive full credit, okay? So this is important. Your derivation should demonstrate that you understand what a double precision floating point number is, all of its components. Okay, it has got 3 major components. It has got the sign bit, it has got the exponent, and it has got the fractional part of the mantissa in base 2, and the process. Okay, the keyword here is the process of converting a value into the double precision floating point number representation. If you go online right now, if you go to Google and you look for a a tool online where you give it the value and it will give you the hexadecimal representation as a double. I'll bet you that you can find like 3 or 5 of those tools like right away on page 1 of the search result. That is not what I'm asking people to do. I'm not asking people to show me your Googling skill. I'm asking people to show that that person, actually understands, what is going on. So that is why the process is important. Steps such as base conversion, how to work out each component of a double precision floating point number are important. So this is my clue of saying you might want to do a base conversion first, okay? Then you tell me how to break it up into the components or how to come up with the value of the various components in a double. I cannot outline all the steps as that is part of what is being tested. Okay, so that's actually it makes sense to me that I cannot tell people exactly what all the steps are, because otherwise I wouldn't be testing people whether they understand what the steps are, right? Because if I tell them what the steps are, then I'm not testing it. All right, so the number for this particular version of the test is 46.625, and then use the following space to type your answer. So one more thing that is important, and I know that I'm going to write it down, before Thursday, so the people who are not currently here, and we only have about 9 or 8 people, in class, who are listening to this live. I think some people on the YouTube side, so we might have about 10 people. But it is important to write down the steps step by step. Okay, please do not copy and paste. Okay, because that is not a good way to do it. Now, if you have to write it down on a piece of paper and then use a cell phone or some other way to take a picture of that and then paste it into the answer over here, that's actually okay, because when you're handwriting, it's perfectly fine. Okay, I just do not want people to digitally copy and paste into the answer area. Okay, so what we'll do is, and you don't have to use all the superscript subscript stuff, because that takes up a lot of time to find out how to do the superscript subscript. So what we can do is we are just now saying that 46.625 in base 10, and just do it this way. Okay, in parentheses 10 means the number is in base 10. In parentheses 2 means the number is base 2. In parentheses 16 means it's hexadecimal. You can always use 0x as a prefix of hexadecimal, because I understand that as well. And if you do not give me any base indication, it is by default a base 10. So in this case, if I were to just do this, it would be exactly the same as explicitly saying that it is a base 10 number. All right, so what we'll do is we're going to break it up into a summation of powers of 2. So if I were to do this manually, okay, by hand, then I'm going to do it like, okay, we got a 32 in 46. After we take the 32 out of 46, we got, what, 14 left? So of the 14, we got an 8, and then we got a 6, so that has a 4 and a 2. And then we got the fractional side, which is 0.625. And in 0.625, there's definitely a half, which is a power of 2. And then once we take care of that, we do not have a quarter, but we do have an eighth, which is 0.125. So you can see how I can just do this kind of manually. And there's no need to actually explain how I got the 32, how I got the 8, why 16 is not here, and so on. Just breaking it down into a sum of powers of 2 is good. Okay, so now we can say, this is 2 to the power of 5, that's 32, and then we have 2 to the power of 3, then we have 2 to the power of 2, then we have 2 to the power of -1, and then we have 2 to the power of -3. Now these are all in base 10, at this point, but the next line is where we do the conversion into base 2. So we got 1 followed by 5 zeros. That's 2 to the power of 5. So that's in base 2 now. And then 1 followed by 3 zeros. That's our 8 in base 2. And then we got our 100, which is our 4 in base 2. And then we got, I think I missed one of them, didn't I? Yep, I did. Okay, I was missing 2 to the power of 1. So I missed that one earlier. Then we got a 1 0 in base 2, that's our 2. And the tricky part now is, what about this 2 to the power of negative 1? Yep, Catherine is correct about that. Okay, very good. So now I have the fractional part, which is 0.1 in base 2. So, 1 of, it has this 1 over here. But when we have a power that is on the negative side, then they're all to the right-hand side of the decimal point. And we do not have a 0.01 because that is going to be a quarter. A 2 to the power of negative 3 is 0.001 in base 2. And that is our 1/8. Okay, so where the 1 is, okay, how many digits it is to the right hand side of the point is how negative it is in terms of the power. So now we have all of these, we just kind of add them up. So we got 1 0 1 1 0. I'm missing a 0 somewhere. We got 16, okay, 32, 16, 8, 4, 2, and then a 0 over here. Yep, okay, 0.101 in base 2. All right, so that is base conversion. So now we have to work with this and figure out what is the exponent and also what is the mantissa in base 2. So you can now kind of copy and paste, which is one nice thing about using an editor, okay, is that you can just copy and paste. So now we look at this, and if you want to combine all the steps in one, that's fine too, which is basically saying how many times you have to shift the binary point until we have a normalized mantissa. So we have 1, 2, 3, 4, 5. We have to shift it by 5 places. Okay. But when we do that, we have to now say that, well, let's compensate it because we have just shifted the binary point 5 times to the left-hand side. So we have to multiply the number by 2 to the power of 5, because every time we shift the point to the left by 1 place, we are dividing the value of the mantissa by 2. So in order to preserve the value being represented, we have to use an exponent portion in base 2 to make up for the shifting of the points. So once we have this part, then we can now say the sign is a 0 because it is non-negative or positive. We can now say the exponent of 2, okay, E2 is 5. But E2 being 5 means that E, which is the biased version of the exponent, is 5 plus 1023, and that is 1028, which is 1024 plus 4, which is 1 followed by a bunch of zeros. So I'm going to put in all the zeros first, and then I find out where I need to change a 0 to a 1. So we need 10 zeros because 1024 is 2 to the power of 10. So we have to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then the position corresponding to the 4 needs to be a 1. This is a 1, this is a 2, and this is where the 4 is. Turn it into a 1, and now we have a binary number for the exponent, the biased exponent. And then the mantissa is this entire thing. The normalized mantissa is the entire thing, but then the fractional part of the mantissa, okay, fraction of mantissa is 0.01110101, and that's in base 2. So now when we put the whole representation together, okay, so this is double representation in base 2. We have the sign first, and then we have the exponent, the biased exponent, which is 1 followed by 7 zeros. 1, 2, 3, 4, 5, 6, 7, and then 1, 0, 0. And then we have the fractional part of the mantissa, which is 0, 1, 1, 1, 0, 1, 0, 1, and then a whole bunch of zeros after that. Okay, so we can use that shorthand. So now we have to look at groups of 4 of these things. So we say this is the same thing. Okay, this is where copy and paste comes in handy again. So this time we want to group things by 4 bits. Oops, I just pressed the wrong key on the keyboard. All right, so we group it by 4. Here's a group of 4, another group of 4, another group of 4, and so on. So now we look at the representation. We got a 4 here, and we got a 0, we got a 4, we got a 7, we got a 5, and then we got a whole bunch of zeros. So now we can say the hexadecimal representation of the doubles bit pattern is 40x40475, and then we just have to make up with a whole bunch of zeros. So there are 16 digits altogether. These are 5 of them, so we need 11 zeros after this. So we have to count again: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There we go. So this is what I mean when I said, do it step by step and show me that you understand what it is, what is the representation, and what it takes to convert it. Okay, because there are tools out there that can give you the final answer like that. Okay, just snap and you're done. That is not going to get anyone any points, because my test is not about Googling skills. It is about each individual's ability to understand the material and apply the knowledge. So this is what I mean when I ask for a complete answer that is step by step, and it demonstrates. The key point is your answer has to demonstrate your understanding of the material and your way of solving a problem. So are we good with this one? Shall we continue? Okay, I'm not seeing any feedback here. All right, so let me save this, and I'll use ODF format, save, and I'll put it into Discord. There we go. And I'll pin it too, so this way you can quickly locate things that you can download. All right, so that's one question. Let's work on a different question. Another one that is, I think, more interesting. So question number 2, the last time I gave this exam, looks like this. So let me change the format first. We want to use web. There we go. So this way I don't have to handle the horizontal scroll bar all day long. All right, so this question, on the other hand, is about implementing a new opcode. Okay, so we haven't really talked about return yet, so I'm not going to mention the word of return. So instead, I will give you just this part here. So there'll be multiple slices to this instruction. The first slice just needs to do this. Now, you don't even have to ask me why we are doing this. I'm just telling you that this is what this particular slice needs to accomplish. And it will have other 2 slices too. So the second slice needs to do this, okay? And the third slice needs to do exactly that. So I'm already telling you what each slice needs to do in terms of which register is getting what, okay? And by the way, when we specify how a processor works, and the way we express it is documenting it by saying which register is getting what kind of value. It is called a register transfer language, or RTL, and it's a very specific language for describing how processors work. Okay, so if anyone wants to look it up, it is called RTL, or register transfer language. But that is not even important to us, because if I tell you that we need a slice of the ROM that needs to do this part here, where are you going to go look? How do you approach this question? Okay, let me see. Oh, Discord just crashed. Okay. There we go. So we are back. And I have to reshare the screen. Discord just crashed on me. And here's OBS. Go live. There we go. Alrighty. Alright. Yeah, YouTube is still going because YouTube is completely independent to Discord. But Discord obviously is not the most stable application. There are other times where Discord does not crash, but it will just chew up all the processing time, so everything goes like super slow when that happens. So anyway, getting back to this, and I'm going to restart the discussion just a little bit. Okay, so it looks like we're missing about 3 minutes worth of stuff. All right, so we'll restart from that point. So this question is really asking, okay, wrong key. So this question is really asking, if I need to do something like this, b equals to star d, how would I initialize all the bits? Now, I'm giving you a proposed solution, okay? But you need to make certain changes when it is wrong. Okay, so that is what this question is about. I'm already telling you this is the job of this slice. Okay, slice 0 is supposed to do this. This is question number 2 when I had the last exam. This is question number 2. I have not uploaded yet, so I'm gonna upload it after I present the answer. Is that okay? All right. Okay, cool. So the question is already telling you what a slice or what a location in ROM is supposed to do, and it's already giving you a proposed solution, to get it done. So your job is to troubleshoot it. Okay, your job is to look at all the bits that are set here, and then you say, is any one of these wrong? If it is wrong, let me fix it. On the other hand, if something is not wrong, and it can be anything, then you don't want to touch it. Okay, so you have to know when to make a suggested change and when not to make a suggested change. And when you do make a suggested change, you have to indicate why you're making that change. All right. So to answer this question, there are many ways to do it. Okay, if you just look at the static picture of the processor, that will give you, enough to do it. Okay, you don't even need to have Logisim up and running. On the other hand, if you can get Logisim up and running, well, that can be very helpful. Okay, so let me show you what I mean by that. Let me see. I'm just doing some stuff off the screen so I can get back into Logisim. Okay, 1978. All right, so let's go ahead and reload Logisim, and this time we are in the GUI mode. All right, so this is Logisim in GUI mode. So the first way to answer this question, which is probably it's helpful in many ways, but it is not going to give you the entire answer either. Okay, is to look at this and go like, well, do we have any existing slices that can already tell me how b equals to star d needs to do? How should we configure all the components in the processor and RAM in order to accomplish register B is getting whatever in RAM that D is pointing to? Well, what do you guys think? Do we have a current instruction that can do this already? So this means that you need to study the opcode table. Okay, so the opcode table, when you look at the C notation part, that exactly, so Richard has got it, but I'm just telling the whole class, how to get ready for the test, is really to go to the opcode table and know how to read the opcode table. So when you go to the opcode table, and it's right here, so you have to look at column C, which is the way that I describe what an instruction does, and then you want to make a match to what we are looking for. So the one that we're looking for is x equals to star y. So when you look it up, you see, where is it? The way I organize, the opcode is kind of random. Okay, there we go. So we have just found it. So we know that LDX in parentheses Y would accomplish exactly the same thing, where X is where the register that is getting updated, and Y is the register that points to the location in RAM where we grab the value in order to update X. Okay, so we already know this instruction exists. So if the instruction exists already, we can kind of take a little bit of a shortcut to answer the question. So the shortcut involves doing something like this. Now this is all getting recorded, so don't try to copy or describe in text right now how to do it. Instead, in your daily log, you might want to just kind of note the time, which is 9:56, 34, 35-ish. So this way it's easier for you to get back into the recording. Then you have all the time in the world to write down the step-by-step instruction if that is what you want to do. Okay, so don't try to write down instructions along the way, because you will not be able to write down instruction as fast as I can talk. But after the class is over, then you have all the time in the world to review what I did. So the way to do it is to hijack not to hijack, but to inject the code that we need into microcode pointer itself. So now we have to go back to the question a little bit. Okay, the question is b equals star d, and then we have to go back to the opcode table. So x is b, which is a 0, 1, y is a d, which is a 1, 1. So we have 0, 1, 1, 1, 0, 1, 1, 1. So we have 7, 7 as the actual opcode. So now we switch to Logisim, and then we go to the microcode pointer. The way the microcode pointer works is the most significant two hexadecimal digits should be the opcode itself, and the least significant digit in hexadecimal should be just a 0. That will get us to the slice of ROM that implements that specific instruction right away. I don't even need to write some code in assembly, get it assembled, download the RAM file, and then load it into RAM. I can just inject it into here right away. So I just say 770. Okay, that's exactly what I type on the keyboard, which is 770, and we get to this point already. So if you look into this, it is really great, because it tells me, what is being used to drive the address port and who is paying attention to the D port. So it's the same kind of analysis that we did, before. When I talked about instructions, really step by step, transition by transition. So except this time, you kind of have to, you should have the skills already to figure that part out. Okay, so the more you do this, the faster you can do it during the exam. So part of quote unquote studying is to look at an instruction and go like, okay, I want to figure out how this instruction works, and then just do it by exactly what I just did, and then track it down. Okay, so now how do we get the answer? Okay, the way we get the answer is, oh, RAM cell is a 1 and RAM load is a 1, and then you go back to the question. Okay, so let me switch back to the question over here. So we know RAM cell needs to be a 1, so we basically say a correction. This needs to be a 1. Okay, and we just say that RAM is needed. Okay, because we are retrieving a byte from RAM. Okay, so RAM load is a 1 is good. What about IREN? Okay, so you also have to fix things that are wrong. Okay, well, actually this is something that is wrong, so we need this to be a 0, 0. Okay, we are not supposed to change the instruction register. Now if you do change the, actually I take it back, because even if you change the instruction register, it would not be wrong, because it's not going to do anything. When is RAM not needed for an instruction? That's what Catherine is asking. So I'm going to answer that question in Discord, because I don't want to type over the answer at this point. So I'm just going to type over in Discord, but I'll also kind of word it as well. So increment, decrement, CPR, which is copy register, CMP, which is compare register, JMP without the I, JMPI. Oh, I take it back. JMP is the only one. JMPI does not qualify for this. Let me see what else. All the arithmetic operations. So we got and, or, add, subtract. Okay, those are all the instructions that do not need RAM because they perform operations strictly using registers. Now there are two more which are kind of trivial. These two, no op and halt, they don't even use registers. Okay, they don't use RAM, they don't use registers. They are just, one is just saying that pretend I'm not here, we are not going to do anything, and the other one is saying, okay, let's stop everything. So they do not access RAM either. Okay. All right, so getting back to the question, IREN is technically not an issue because even if we change the instruction register, as long as we don't put that into the microcode pointer, everything is still going to work okay. Okay. Register in enable needs to be a 1. Okay, so this needs to be a 1 because we are going to update register B in the register bank. So it needs to go from a 0 into a 1. And register input select also needs to be changed. It needs to be changed to a 1. Okay, we are updating register B, not register D, because 3 specifies register D to be updated, and we just want to update register B. So this is how we answer the question. Really just kind of go through every single one of these entries and see if it is already correct. Okay, like RAM load was a 1 already, so don't say anything, it is already correct. This one is inconsistent with what we see in Logisim, but because it is actually quote unquote okay, it does not it's not wrong. Okay, if it is not wrong, don't change it. So this is actually going to be the trickiest part of answering questions like this, is not to blindly copy whatever is in the processor simulator into the question, but you also have to figure out, does it matter? Okay, and I'll show you something that also does not matter in this case. ALUEN is a 0. Okay, that is correct. Okay, we are not performing any ALU operations when we just want to grab the content at a location in RAM and copy that to a register. So this is fine. But if the ALU is not even enabled, does it matter which operation are we specifying to the ALU? The answer is no, it does not matter. Okay, it can be 5, it can be 2, it can be 1, it can even be 6 or 7. Okay, where there's no actual matching operations in the ALU. It doesn't matter, because if the ALU is off, it doesn't matter what operation you're specifying. But if you look into Logisim, Logisim always has a specific value for the ALU operation. There's always a value. So if I click on this wire, it specifies that we have ALU operation 0, which we know as add, inside the ALU. So if somebody is to go back to the answer here and say, 0, then I will mark it wrong, because you do not need to change this. Okay, there's no necessity whatsoever to change ALU OP from 5 to 0. So this would be marked incorrect, because it is telling me that one person, the person who is giving me this kind of answer, is not really understanding what ALU OP is about. Okay, so that's why we have to leave this one alone, even though the value of 5 is not consistent with what you see in the emulator. Is that okay? So that's kind of the stuff that we have to do kind of step by step, okay, to go through this. And now we have to ask, do we need to enable register output 0? Okay, so you have to go back to this diagram and ask, well, do we actually need our register output 0? This is register output 0. It goes to a demultiplexer, and then the demultiplexer goes, you can use it to drive the data port, but that's not what we want to do. We do not want this demultiplexer to drive the data port. Now this is really important. If I click on this wire, you can see how the output of this particular demultiplexer can drive the very same node that RAM is driving at this point. So that means if I enable register output 0 and actually select output 2 as the active output of this demultiplexer, I could have caused a problem. Okay, so we definitely do not want register output 0 to be enabled. So if we go back here, it is already, oh, it is a 1 to begin with, so we have to say it is a 0. Okay, we are not using register output 0, and if we're not using it, then whatever we want to specify as register output 0 select is fine, because this is just specifying which register in the register bank is being output as register output 0. Well, since it's not even utilized, we can just say, well, whatever we specify is fine. So do not change this 3 to a 0, because it is a 0 at this point. Because if you look at register output 0 select in the emulator, there's always a value here, and I believe it is usually 0 by default, but we don't want to change the answer to a 0 because that is not necessary. And if the demultiplexer is off, it doesn't really matter which output you select because it's not active. So you can just leave this 3 as is and leave this 0 as is. Okay, so now we look at register output 1, which is actually important. Okay, do we want register D to drive register output 1? The answer is yes, because register D is supposed to specify which location of RAM I want to access. So that is important. But now we need to determine this for this particular demultiplexer, do we want register output 0 or do we want output 1? If we select output 1, it is a path to go to the ALU, and we already know that we are not using the ALU, so that basically means register a 0 for this select is the one that we want. So we want RO1 demux to be a 1, to be a 0, sorry. And it is already a 0, so it is already correct. Register output, whoops, I take a, yep, it is already a 0, and we're selecting 3, so everything is good up to this point. And then we go down here. We already talked about ALU. It should be disabled. We are not performing any arithmetic operations. And if it is already disabled, it doesn't matter what operation we are actually specifying because it's not doing anything. Then we look at the address mux. Should it be a 0 or 1? So the address mux is over here. If it is a 0, then we are connecting register output 1 to the address port, which is on the other side of the multiplexer, and that's basically what we want. Okay, I'm just trying to select the pin, the node. There we go. So it is already correct. Address mux is supposed to be 0, so that is okay. And PC mux is a 7. Well, now we have to ask the question, should it matter? In other words, are we supposed to be changing the program counter? And the answer is no. We are not changing the program counter. We are only changing register B. So that means the program counter enable should be a 0. Okay, and we have to say that we are not updating the program counter. So if we're not updating the program counter, it really does not matter what PC mux is, because PC mux influences how we update the program counter. So if the program counter is not getting updated, it really does not matter what PC mux is specifying. So we have to leave the 7 as it is. Okay, so even if in the simulator it is something else, we have to leave it alone. So now we have to look at bit 24 and bit 25 of ROM, which do not have tunnels, and that's why they are not named. So we have to go back into ROM over here, and then we ask, where's bit 24 going? So this is bit 24, and do we want bit 24 to be a 1? If bit 24 is a 1, we are just incrementing the microcode pointer, which is appropriate. Okay, we just want to increment it at this point. So going back to the question, this one is fine. And bit 25, if you remember from our earlier discussions last week, is connected to the reset port of microcode pointer. So if this is a 1, it will turn the microcode pointer to 0, and we are not quite there yet. Okay, so we don't want this particular bit to be a 1, so this particular bit being a 0 is fine. So that answers slides 0, and you basically just have to go through the same process to answer slice 1 as well as slice 2. Do we have any questions about how to go about answering the rest of this question? I'm hoping it is more a matter of spending time. It is a little bit tedious, and you kind of have to know your way around the processor. But other than that, do we have any conceptual questions? Okay, so Jerry is typing something. All right, so I can see how I'd answer. It just seems like this would take a long time for a single problem. Well, when I had this question in the exam, I only got 3 questions for exam 2. The entire exam 2 only had 3 questions. So given only 3 questions and 80 minutes, I don't think it is too long. And that really reflects how well people understand the processor, because as you probably already know, if I am the one who's going to answer these questions, I can probably kind of breeze through it pretty quickly if I don't have to explain things along the way. So it really boils down to how familiar are you with these individual tunnels, and do you know when each one is actually needed and when it is not needed, or what it specifies has no importance. So that is basically how you prepare for the exam, is you kind of go through all the instructions and understand for each instruction what is it that it does and what does not matter when we want to perform that operation. And those are all the things that you can prepare before the test, is to get familiarized with the processor. So you don't want to do exactly what you just did, like code the first time during the exam. You want to have done it multiple times already, so that you can, when you encounter something like this, you can kind of go down this list and know that, yep, okay, this one they need a 1, this one they need a 0, and so on. Any other questions related to this question? I'm just turning on a screen capture tool. All right. So do we have any other questions about this one? Because if not, I want to kind of move on. We only got about 10-ish minutes left. Okay. Okay. So what I want to go through, with the rest of the time here, is what other questions I might be asking. So I can give you the code to perform a particular operation, like finding the absolute value, except the code that I provide to you has a bug. So your job is going to be fixing that bug. So you're not supposed to rewrite the entire program. In that case, you're supposed to pinpoint which instruction is incorrect and what it should be changed to and why that is the case. So there might be questions about debugging. I wrote down something a little bit earlier today, and I just need to pop it up on the screen right now. There we go. X2Q. Yep, there we go. All right, so I might ask you a question. Now, I cannot show you a sample question because I have never asked a question like this before. So this might be the first time that I will ask a question like this. So with regard to memory devices, like the SR latch or the D flip-flops, I might give you a scenario where I describe the state of every single gate in the device, describe the output of each input pin as well as each gate. But then I'm asking you, do you see any conflicts? Do you see any problems? And if you see a problem, tell me why it is a problem. Tell me why this gate cannot be outputting this particular value. Okay, so there might be a question like that. Okay, you're troubleshooting a snapshot of a particular device that we have talked about in this class. It can range from SR latch to any one of the D flip-flops. So I cannot show you an example because I have not asked this kind of question before, but you can kind of imagine what it will look like. I'll give you the states of the input pins. I'll give you the states of each specific gate or each device in the design, and I'm just asking you, okay, do we have a problem here? Okay, the output of which one of these devices is inconsistent with its inputs. So how would we evaluate the last two gates in the SR latch? All right, so that's a very good question. So we know that. So this has to do with constraint-based kind of reasoning. You basically have to rule out certain impossible cases. I'll give you an example. Under what circumstances will both Q and NQ be ones? Well, it's possible, right? It's possible, but when does it happen? Exactly. So Richard has got it right. If the S and R are both zeros, then both outputs are going to be ones. So now the next question is, can we have both outputs of an SR latch being zeros? The answer is no, not as a steady state. Okay, in the oscillation state, yes, it is possible, but it cannot stay for long. But I'm not going to ask you tricky questions about transient states of a gate. It's going to be a steady state. In other words, it's stuck like this. Okay, if I don't do any more changes to the input pins, this is where the circuit is going to be like statically. So those are the constraints. If one of the input is a 1, excuse me, let me take it back. If one of the output of an SR latch is a 1 and the other one is a 0, then we have a little bit of flexibility there, okay? But it will still rule out some of the options. Let me show you what I mean by that. And to do that, I'm going to use, this would be a good place to put it. Okay, so if I give you a scenario, okay, so what is given is the SR latch Q is a 1, and then the NQ is a 0. Okay, so basically this is the given condition, and I should use double equal to basically say that this is the state. I'm not changing Q to 1, I'm not changing NQ to 0. It's just that Q is 1 and NQ is a 0. Okay, so based on this observation of the output, what can the inputs be? Okay, so we'll look at the possible input states. Okay, possible inputs. So one possible input is the set is a 0. Okay, so the S input pin is a 0, and the R is a 1. Okay, SR dot R is a 1. That's 1. And the other one is just both being 1s, because this can be a memorized state. Okay, so it is possible that we have already set the SR latch to this state from before, and currently we are just in the maintenance mode of having both inputs being 1s. So that tells us that the input cannot be both zeros. Okay, it also tells us that the input cannot have S being a 1 and R being a 0. So it already helps to constrain us to only 2 of the 4 possible inputs. So if these are not consistent with what is feeding into the S and the R pin of an SR latch, then we don't have a problem. Okay, so is that answering Catherine's question? It's basically using whatever is given to you to logically deduce and use constraints to help rule out this cannot be the case. Okay, because this constraint here says only these 2 things can happen, and those output says that this can happen, and they are conflicting. So we are applying that line of reasoning to spot the problems. Okay, excellent. So that gives you one question, and then for the double, I have just illustrated one particular one. And because last time I think a lot of people just went online to some kind of calculator to work on that, so I will change the format of the question a little bit, but it will still be testing exactly the same stuff. It's just that the format itself is going to be a little bit different. but it'll still be asking basically about knowledge of double representation and the process of working out the binary representation, or given the binary representation, work out the actual value being represented. So in terms of processor architecture, question number 2, which we just kind of went through, is not a bad example. So I'm gonna stick to that one. And then with assembly language coding, I cannot give you the sample question from last semester because it includes some material that has to do with subroutines that we have not talked about. So if you think about it, it's going to be not related to C code that much. It's going to be more or less along the line of finding the absolute value of something, in terms of complexity. So I'll tell you what the code is supposed to do, and you have to kind of go through it and find out whether it's doing what it's supposed to, or if it's not, then you have to figure out what's wrong with the code. But remember, unlike a face-to-face test on paper, you do have the assembler, the trace analyzer, and also logisim available to you in order to try to figure out the answer. All right, so I think we are running out of time. So we can continue. I can continue to give you a little bit more examples maybe tomorrow, but we do need to move on to new material that will not be in exam 2 tomorrow and also on Wednesday. The exam is scheduled on Thursday, so I'm still collecting time conflict information just like last time, and then by tomorrow I'll have hopefully I'll have everybody turn in by tomorrow. Then I'll give you guys an idea of what time slots will be available. So my idea is to make sure that every person can make it to at least one of the time slots that I'll be offering on Thursday, and then we'll go from there. Do we have any additional questions before I stop the live stream? There are no new labs today because we just talked about past exams, so there are no new labs. And I'll be uploading the other question so that you have a copy of that too. But before I stop live streaming, I just want to make sure that we don't have any additional questions at this point. All right, I'm not seeing anything. All right, so I will stop the live stream, but oh, okay, Richard is typing something, so no, well, that won't be tomorrow's main objective. But if you guys have any questions to ask, we can answer. I can answer those questions both tomorrow and also the day after tomorrow. So anytime before the exam, I can still continue to answer questions related to the topics related to the exam. In fact, if you have questions about any material that we have talked about up to this point, I'll be answering those questions. Now, granted, I might answer some of those questions with questions, but I will, answer those questions. All right, so this is the microcode sample question. Okay, here is something that you guys can do. I think this is going to be helpful. I did not fully address the entire question for the one that I'm just uploading right now. So one thing that you guys can do, okay, is to work on slice 1 and slice 2, the last 2 slices. Okay, so work on that, okay, as an ungraded homework assignment, and then tomorrow I'll work that through so that you can compare your answer to what I have, so that you have a better idea of what I'm looking for and also how to answer that question. I think that is probably something that it's productive for you guys to do. So are there any questions about that recommendation? It's not something that you have to turn in, but I think it will be very helpful. No questions? All right. So somebody can remind me tomorrow to go over the question that we are seeing right now, okay, and specifically how to answer slice 1 and slice 2. So we'll start tomorrow's lecture by this little exercise, and then we'll have to move on to talk about concepts in translating code from C into assembly code. So are we good? All right. So I'll be online until about noontime, but then I have an appointment at 12:30, so I'll have to leave the house by 12:15. But I'll still be answering questions, throughout the day. It's just that I won't be, I'll be AFK, as they say, for a little bit. All right. If there are no additional questions, I'm gonna turn off the live stream. And I'll just be on the text mode. Oh, you're welcome. Thank you.